Our second lesson in trig ratios is working with special angles, developing the unit circle, and applying the unit circle to some questions. So we know how important it is to work with trigonometry, and trigonometry exists all around us. Being able to do simple calculations with trig is very important. So we're going to take a look at this little example right here. It's asking us for the exact equivalent of 45 degrees in radian measure. And if you recall from the previous lesson, if we're converting from degrees to radians, we would multiply by pi over 180. 45 pi over 180 reduces to pi over 4. If we want to calculate this on the calculator, and we want to calculate the sine of pi over 4, then this involves making sure our calculator is in radian mode, which mine is, and then simply typing in sine of pi divided by 4. And the answer is going to be decimal 7071, which is the same answer if I change my mode back to degree and type in sine of 45. The values should be exactly the same. These refer to the y value. So when x is pi over 4 or 45 degrees, the y value is at decimal 7071. Similar examples can be found by taking the cos of pi over 4 and the tan of pi over 4. Now sometimes you may want to find the reciprocal trig ratios. So say for example we just worked with sine of 45, or in our example it was the sine of pi over 4. What if we wanted to find out what the cosecant of pi over 4 is, its reciprocal function? Well, cosecant of pi over 4 really is 1 over the sine of pi over 4. So let's use our calculator to help us solve that. So on the calculator, we would, once again, I'm going to change my mode back to radian. And I'm going to start fresh here. I'm going to calculate what the sine of pi over 4 is. And then what I want is the reciprocal of that answer. Now on my calculator I have this little x to the negative 1 button. When I press the x to the negative 1 button, it takes whatever my last answer was and finds the reciprocal of it. And so the answer for cosecant of pi over 4 is going to be 1.414. 1.414. And that's usually the easiest way to determine it. Make sure you are taking the reciprocal of sine of pi over 4, not just pi over 4. Alright, now that we've established how to plug these numbers in the calculator, let's get to the main part of this lesson, and that is to clarify and discover what the unit circle is. Now we are going to be using the unit circle in a variety of ways. It may be used simply for evaluating, say, the sine of 5 pi over 4 and finding the exact value of it. It may be later on when we use identities and you're asked to evaluate the sine of 3 pi over 4 plus pi over 3, and we need to expand that using something called the compound angle law, which we'll learn later, and then pull the numbers off of the unit circle. So the unit circle is set up, and I'll do a quick sketch of it here, and then we'll only look at the first quadrant, and then we'll look at the second, third, and fourth. Because it's a unit circle, we know that the radius is 1, so all of these lines have a length of 1. So the first line at 0 degrees or 0 radians is going to have a coordinate point of 1 and 0, so 1 comma 0. The next part of the unit circle goes up by really what our special triangles are. So the first angle we're going to look at is 30 degrees, then 45 degrees, then 60, and then up to 90. Now I'm going to rewrite each of these as their radian form. So 30 degrees is the same thing as pi divided by 6. And again, remember that it's 30 multiplied by pi over 180, which reduces to pi over 6. And if we continue moving up the ladder, so to speak, 45 is pi over 4, and 60 degrees is pi over 3. 90 degrees is pi divided by 2. So these become somewhat standard, and we start to recognize these. What we want to do now is find out what the coordinate points are. And we're going to use the combination of a method we talked about in our last lesson, where x and y, given an angle theta, can be written as cos theta sine theta. And so when we move back to the unit circle, to find the value of, really this is cos of pi over 6, we can go to our friends, those special triangles, to help us determine it. And so whatever the ratio of cos of pi over 6 is and sine of pi over 6 will go in for the two coordinate points. And so that's what we're looking at. So we're going to now just slice out this, this first quadrant, quadrant 1, and fill in these values. So let's go to a clean slide right here. So I'm going to copy down my angles. That was 0 degrees, that was 30 degrees, 45, 60, and 90. And then rewriting in the radians. Remember radians, if there's no units, we assume it is in radians. Pi over 6, pi over 4, and pi over 3, and finally pi over 2. Now the two easiest coordinate points for these are going to be 1 and 0, and because this has a height of 1, this will also be 0, 1. So we can fill those in right away. What we don't have is these other. So let's start to develop this one. On the previous slide we talked about the first spot here being represented by the cos of pi over 6. So for a moment, let's envision the special triangle in a right triangle that has one angle of pi over 6. Now pi over 6, if you want to do a quick conversion, is 30 degrees. This would mean that this angle has to be 60 degrees or pi over 3. Special triangles say that when this is 30 degrees, the opposite side has a ratio of 1. 60 degrees or pi over 3 would have a ratio of root 3, and the hypotenuse, which is the longest side, would have a value of 2. So therefore the cos of pi over 6 is going to be root 3 over 2. And the sine of pi over 6 is going to be opposite over adjacent, which is 1 over 2. And there's our first set of coordinate points. And we're going to do the same thing when we try and determine the other special triangles for 45. So we can draw the 45 over here. So theta is 45, or pi over 4. And this is 90, and this will also be pi over 4. The ratios for these triangles is going to be 1, 1, root 2. So the sine of 45 and the cos of 45 are both 1 over root 2. 1 over root 2. Now, we're not going to leave these with a denominator of root 2. In grade 11, you would have learned how to rationalize. And so when we have a question like this, and you have 1 over root 2, rationalize means we don't leave radicals on the bottom. So to rationalize, we multiply top and bottom by the equivalent of 1, which is root 2 over root 2. Root 2 times root 2 is equal to 2. And if you think about it for a second, square root is the same thing as 2 to the half times 2 to the half. But when the bases are the same, you add the exponents. This becomes 2 to the 1/2 plus 1/2, which really is equal to 2 to the 1. So that's why square root 2 times square root 2 equals 2. And on top, we actually do have a root 2, and that's fine. We can have a root 2 on the denominator. So we are going to erase these, and we're actually going to write in the rationalized versions of them. I'll put them in black. So it's root 2 over 2 and root 2 over 2. The last coordinate point that we don't have any information for is 60 degrees or pi over 3. So let's look at the triangle from pi over 3. So the cos, which is the first term, cos of pi over 3 is 1 over 2, adjacent over hypotenuse. The sine, because remember the second coordinate point is the sine of pi over 6, that's going to be root 3 over 2. And there's a couple little reminders here. If you take a look what we have, and we work moving down, we have the numbers 1, 2, 3. And if you take the square root of all of these, square root of 1 is 1, square root of 2 is here, square root of 3 is here. And on the opposite side, on the y value, you have 1, 2, 3 again, and notice the radical signs. The denominators of all of these are 2. So there is a little pattern going on here. Now what we're going to do is we're going to take a look at the second quadrant, and starting at the second quadrant we're going to start to look for patterns so that we can fill this in much quicker. The positive and negative here, both values x and y are positive, so if you think of the cast rule, this is the quadrant that both primary, sine, cosine, tan, and reciprocal, cosecant, secant, and cotangent are positive. There are no trig ratios that are negative in this situation. They are all positive. Okay, so I have a diagram here that we're going to work with. If we call this angle right here pi over 6, 30 degrees, and we fill in the remaining angle, say that's 45, and that's 60. The next one that we would have over here is 30 degrees from the y, 45, and 30. And so what we have to understand is that this pi over 6, if we were to use the y-axis as a reflection piece, this angle of pi over 6 is the same as this angle here is pi over 6. And this angle of pi over 4 is the same as this angle is pi over 4, and so forth. So that's going to help when we start to determine what the coordinate points should be at each of these spots over here. And remember there's one more over here, but I think you've probably figured out that that's minus 1 and 0. So what we want to try and take a look at is, I'm just going to write out the coordinate points that we had on our last slide, and if we flip back the values that we started with, we're right here. So it was, oh, there it is. The values we had were root 3 over 2 and 1/2. Root 3 over 2 and 1/2. We had root 2 over root over 2 and root 2 over 2. And then we had 1/2 and root 3 over 2. So I'm going to look at this coordinate point next. Now, here's what I know. The number of degrees to this point is 90 plus another 30, which is 120 degrees. The angle down to the negative x-axis has to be 60, because 60 and 120 make 80. Well, that's the same angle here. So let's just take a look on the calculator. What I want to do is I want to evaluate. I'm going to use degrees in this case. I'm going to evaluate the sine of 120 and the sine of 60. So here we go. So I'm going to change my mode back to degrees. And I'm going to do that calculation. So sine of 120 gives me decimal 8666, and the sine of 60 gives me exactly the same number. So these two are equivalent. And the reason I showed you that is because what we're going to do is we're going to drop a line straight down from 60 degrees to form a right triangle. And that right triangle is going to allow us to solve for these coordinate points. So if I was able to find out the cos of 120 degrees, that is equivalent to the cos of 60 degrees. And if I were to find the sine of 120 degrees, that's equivalent to the sine of 60 degrees. And I'm using these acute angles because I can draw a special triangle here. So the special triangle that I'm thinking of looks something like this, where this is pi over 3, 60 degrees, this is pi over 6, 30 degrees, and I have to remember that I'm in quadrant 2. So when I'm writing out my ratios, opposite of 30 degrees is 1, but because I'm in quadrant 2, that x value has to be negative. Opposite of pi over 3 is going to be root 3, and I'm going to be 2 here. So the cos of pi over 3 is adjacent over hypotenuse. The sine of pi over 3 is going to be the opposite side over the hypotenuse. So here are my two values for my coordinate points, negative 1/2 and root 3 over 2. They go in right here, negative 1/2 and root 3 over 2. Now I want you to take a look at the numbers on the flip side of it, and by flip side I mean reflection. If I were to take this point and reflect it over the y-axis, I end up here. And notice what the values are. Well, what we've done is we've gone the same distance to the right as we've gone now to the left. And so the x value is 1/2, the x value here is negative 1/2. The y value is the same thing, and we haven't changed the height at all. So if you use that same method, then I should look across and see that instead of the positive x value here, I should have negative root 2 over 2 and the same y value. And the same thing here. The x value should be negative, negative root 3 over 2 and 1/2. So all of the x values should be positive here, and that holds true with the cast rule as well. Because one thing that the cast rule says is that all of the trig ratios are positive here. The only trig ratio that's positive in this case is sine, and if you notice, the second coordinate points are all sine. So that holds true. So cast rule does come into play. Now if we use this same sort of patterning that happens, you can probably predict what's going to occur when you start to draw this line reflected, the 45 or 135 degrees, and then finally the last one. So let's just take a look at the one example, and then we'll start on a new page and make this nice and clean. So this angle right here and this angle right here are the same. So let's see what's happened. Well, the x value hasn't changed. They're still the same distance away, so that's going to be negative root 3 over 2. The y value, so instead of it being positive 1/2, it's now gone down 1/2. And that kind of makes sense because in quadrant 3 we have negative x values and negative y values. So take a second now with the blank sheet that we were provided with in class and fill in the remaining two spots. I'm going to pause the video here, bring back a much cleaner copy of this, and then we'll continue with our last coordinate. So here we have a somewhat completed 3 quadrants anyways of the unit circle, and again looking at the values in green that give us our coordinate points. So if you were very quickly asked what the value of the sine of 4 pi over 3, your answer is negative root 3 over 2. If you were asked what the cos of 150 degrees is, your answer is negative root 3 over 2. You can just pull the values off. Cos, sine, cos, sine, cos, sine, all the way through. So let's complete this. At 270 degrees, we've gone 0 units left or right, but we've gone down 1 unit. And now we're in quadrant 4, where all the x values should be positive and all the y values should be negative. So let's take a look at what happens. So the x value gets shifted over or reflected, so it should become positive, so that should be 1/2 and still negative root 3 over 2. Negative root 2 over 2 becomes positive root 2 over 2 and negative root 2 over 2. And finally negative root 3 becomes positive root 3 over 2, and minus 1/2. The last example, once we get to 360, we've gone fully around the circle, so that becomes 0 radians once again. And this is our unit circle. You're very familiar with the first quadrant. That's in grade 11. Some of you may have completed the second quadrant in grade 11, but we are responsible for knowing all of it. So I'm just going to put in the radians here: 2 pi over 3, 3 pi over 4, and finally 5 pi over 6. So remember, degrees to radians are found by that simple calculation. Now this does follow the cast rule, where the fourth quadrant is C, the first quadrant is A, S, and T. And if you follow through, all of the cos values, which in this case are all the x values, should be positive. All the values, cos and sine, should be positive, and all the sine values, which are the y values, should be positive. And in tan, in the third quadrant, tan is positive, which is sine over cos. Remember that trig ratio from grade 11, tan is equal to sine over cos. So it is very important that we have an accurate unit circle, because we will need to use it. And we're going to take a look at some questions right now that involve the unit circle. So let's look at this word problem. It says Ravinder is flying his kite at the end of a 50-meter string. The sun is directly overhead. The string makes an angle of pi over 6 with the ground. As the wind speed increases, the kite flies higher until the string makes a steeper angle of pi over 3 with the ground. Determine an exact. That word is very important. That means we do not have to use the calculator. The only time we have to use the calculator is when we're asked for a decimal, or to the 10th or 100th of a meter. So we want to find the horizontal distance that the shadow of the kite has moved between the two positions. So like anything, a diagram is a very healthy thing to do here. So if we call this the ground, and Ravinder's kite string is going to be at first with an angle of pi over 6, which is 30 degrees. So let's make that about 30 degrees. And then the wind picks up, and I'm going to make this a dotted line. Let's make it a blue line without an arrowhead on it. We don't need an arrowhead. And it gets a little steeper. So the line is the same length, but now it's steeper. So we can tell right away that the horizontal distance has changed. The horizontal distance was way out here. The wind has blown it higher, but back a little bit closer to us. And imagine if the wind is even stronger, the kite might be overhead. What we need to do is we need to draw some right angle triangles that will allow us to use our trig. And so what we can do, I'm going to leave that arrowhead on there, is to label that this angle is pi over 6, and the larger angle, the steeper angle, this whole angle here, is pi over 3. Now, what we need to represent is we need to represent this, we'll call it x2, this distance, and we also need to represent the shorter distance and subtract them. So I'm going to work with just the lighter triangle right now, and I'm going to recognize that I need to work with the adjacent side, and I know that the kite string hasn't changed. It's going to be 50 meters here, and it's going to be 50 meters here. So I'm going to use cos of pi over 6 is equal to adjacent, which is x2 over 50. When I rearrange this equation, I have x2 is equal to 50 times the cos of pi over 6. Once I see a familiar angle, I can go right to my unit circle that I created, and I can determine what is the cos of pi over 6. Sorry, here it is here. So let's take a look. So here's pi over 6. This is the cos value, root 3 over 2. So I simply substitute that back in wherever I see a cos of pi over 6. 50, and it was root 3 over 2. Now I want to simplify this, so I know that 2 divides into 50 25 times. So I end up with an exact expression as 25 root 3. I do exactly the same thing when I'm solving for the shorter side, or shorter length, I'm going to call that x1. So I would take cos of pi over 3 is equal to x1 over 50. Exactly the same process. This time I'm going back to my unit circle and I'm trying to find the cos of pi over 3. Well, here's pi over 3 and the value is 1/2. Take that, replace it, and I have 50 times 1/2, which is equal to 25. Now, the difference between these two numbers is going to be the horizontal distance. So x2, which is 25 root 3, subtract 25. And you might even take it as far as factoring out the 25 and writing root 3 minus 1. That is the exact answer. The 1/10 of a meter, part B, you would actually plug that in the calculator and round to 1 decimal place. So there's a quick example of when the unit circle comes in handy, and that goes for any angle. This question says, using the unit circle, determine exact values of the 6 trig ratios of the angle 3 pi over 4. Well, the 6 trig ratios are the following: sine of 3 pi over 4, cos of 3 pi over 4, and tan of 3 pi over 4. The other three are the reciprocals, so cosecant of 3 pi over 4, secant of 3 pi over 4, and cotangent of 3 pi over 4. So going back to unit circle, we can find the values, exact values for sine of 3 pi over 4 and cos of 3 pi over 4 very quickly. So find 3 pi over 4, there it is, 135 degrees. Here's the cos value, here's the sine value. So it was negative root 2 for cos, and sine was positive. And that goes second quadrant. Sine is positive, cos is negative. Tan should also be negative according to Cast rule. Tan is equal to sine over cos. Root 2 over 2 all over negative root 2 over 2, which simplifies to become negative 1. Cosecant is the reciprocal of root 2 over 2. So 1 over root 2 over 2 is 1 times root 2, Cosecant of 3 pi over 2 is the reciprocal of sine of 3 pi over 2, and I know 3 pi over 4, and we know that value. It's root 2 over 2. When I invert and multiply, I have 1 times 2 over root 2, which is just simply 2 over root 2, but once again, we always want to rationalize. And root 2 times 2 is 2. That's going to cancel out with the 2 on top, so we are just left with root 2. Secant is going to be the same thing, except negative root 2. And finally, cotangent is going to be root 2 over negative root 2, which is still negative 1, and the reciprocal of negative 1 is going to be negative 1. So this concludes a fairly long lesson, but it's an important part of how to derive that unit circle. So we have used our calculator to calculate trig ratios. We've used our calculator to help us with reciprocals. That was the x to the negative 1 button. And then we developed the unit circle and went all through all 4 quadrants using the Cast rule to help us to determine, and there's the keywords, you'll see that a lot, exact values. That concludes the end of this lesson. Good luck with the homework.